Darde Maths. Hello friends, I am Sumant Kumar and you are watching my YouTube channel Darde Maths. And today we are going to discuss the application of second order differential equation. Right? And this is a mass spring vibration, and here I will derive an equation governing the motion of mass spring system, right? And then I will classify this motion into different uh, kinds. Under the certain condition, how will we divide this motion into different part? We will see at the end, right? So here, as we can see in the figure, it is very clear that we have a spring, correct, of length L. Here there is a spring of length L. This is unstressed length, and you can say this is natural length of this spring, right? And K is one constant we called spring constant, right? Spring constant. Actually, this is the stiffness of this spring, right? And this is the positive constant, right? So now this constant is stiffness above of the spring, right? Now the spring is suspended vertically. You can put it in horizontal position also, right? We can place the spring in vertical position also, right? No, but in this problem I am taking it vertically suspended, right? Now an object of mass m is attached at the end of the string, at the lower end of the string, right? And due to this mass, this spring get stressed of length delta L, right? So after putting the object at the end of this spring, the total length of this spring, stressed spring due to mass, will become L plus delta L, right? Now the mass comes to rest. This object come to rest in its equilibrium position, right? So this second figure shows that this is the equilibrium position, right? So this position we may called equilibrium position, right? Where equilibrium position. Now, now what we are doing, right? Now we displace this mass. We can do it vertically downward, or but we can simply, you can say, we can stress this mass or compress. We can extend it or we can compress it, right? We can also compress it, and then released this mass with certain initial velocity, right? Then what happened if we do this activity, right? There will be a motion in this system, and this motion is known as mass spring motion, or sometime we may call mass spring vibration, right? Due to this motion there will be a what there will be we a motion in this system. So we can say that we can construct a mathematical model, right? We can construct a mathematical model on which right, which can that means which will analyze the motion of the object, right? So our question is what, which differential equation or which mathematical model represents mass spring vibration. So our purpose is here to derive a governing equation of the motion, that is mass spring system, right? So for it, see here, after displacing this mass in vertically downward, it get stretched by, get displaced, actually it is displaced by a distance displacement y at a particular time t, right? So let us take this displacement, let yt yt be the displacement, right? Be the displacement of the what? Let yt be the displacement of the object, of the object from the equilibrium position, equilibrium position, right, at any time t, position at any time t. What I am doing, actually I am considering here the this displacement is yt, right? Now for the sake of convenience, right, for the sake of convenience, we are taking this is the equilibrium point, y is equal to 0 is equilibrium point, and this direction, that is downward, right, down as a positive direction, right? I am considering this down as a positive direction. This is the arbitrary, right? These choice are arbitrary. You can choose the upward, right, as a positive direction, right? These are the basically arbitrary. So I am taking here down as a positive direction, right? So now question is here, because here we have a motion, right, a force acting on this system due to mass, right? So what happened? So due by the law, there is a law, and we know that is the very famous law and motion, that is Newton's second law of motion, right? Due to it states that Newton's, so from Newton's second law, we have what we have. This states that force is force equals to mass time acceleration, right? Mass times acceleration, correct? So now this is equal to what? And also we know that acceleration can be also given as the second derivative of displacement with respect to time. So this acceleration can be also given by d2y by dt square, right? So let us say this is equation number 1. Now our purpose is what? Our purpose is to find out the total force which which are acting on this system, right? So how can we find all these forces? So basically we are going to find out the force acting upon the mass, right? So that forces acting upon the mass are what? Right? So basically here there are four kind of forces which are acting on this system. So we are discussing one by one here. So first one is what? Force due to gravity, right? Force due to gravity. So it is just the weight of that mass, right? I mean to say F G stands for gravity, right? So this force is nothing but M times G. This is what? This is nothing but weight of the what you we say object, weight of the object, and this force will act downward, right? This force will act downward. Got it? So this is the first force. Now, second force is what? This is due to the spring, correct? So we can say we can say here this force is what? Restoring force. Actually, this is the restoring force, restoring force of the spring. That means what? That means this force always acts, right? Acts to store, this force will act to store the mass of the object to its equilibrium position. I mean to see this force is given by this force. S stand for spring, and Fs is equal to what? This will be minus K times Y plus delta L. Why I am writing? Because this is nothing but a Hooke's law, right? And Hooke's law states that it states that that means the force, it states that force needed to extend or compress, right? Force needed to extend or compress a spring, right? Compress a spring by some distance, by some distance. Suppose we want to extend a spring or compress a spring by some distance y, then the force needed to do this is is directly proportional to the distance, right? To that distance. To that distance is known as Hooke's law. And this force always, right, oppose opposite in direction. That is, it opposes the direction of the force. The direction of the force. So it means mathematically, if you want to express it, right, you can express it just like F is directly proportional to Y. F spring is directly proportional to Y. So that's why here I am writing F is K, where K is what? K is a positive constant. We called it spring constant, right? Called spring constant, right? But at the equilibrium, why I am taking this distance? See, see from the figure, it is clear that when we want to extend this mass to a distance y, right? So what happened? This due to this mass, already it is stretched to length delta L, and now due to the force, this is extended to y. So total extended length is what? Y plus delta L. That's why I am taking here this length is y plus delta L, and this k is proportionality constant, and this is positive. We called it spring constant, right? So at the equilibrium position, what happened? At the equilibrium position, the total force, right? Total force due to gravity must equals the spring force, right? Exert on this position, right? So mathematically you can say that the net force due to gravity and the spring is zero. So at the equilibrium position, we can say that the net force due to gravity and spring is zero. I mean to say the net force due to gravity is mg, correct? And due to this spring is minus k delta L, and this should be 0. So that is, you can say mg is equal to k times delta L, right? So here it is clear that if we put the value of k times delta L from here to in this equation, therefore what happened? Therefore our Fs, the restoring force due to this spring, will become what? Minus k times y minus mg. This is the force due to spring. Now the third force which is acting upon this system is what? Damping force, right? This is the third force which will act on this system. So the damping force is what? Damping force. So this is, we represent it by F suffix D. D stands for damping, right? So this force is what? This is the friction. That means friction and resistance that the medium exert on the mass, right? You can say this is the force, the friction or resistance, resistance, resistance that the medium, you can say the medium, if we are taking this system in oil or something other medium, then definitely there will be some friction force will work on that system, correct? So that the medium exert on, exerts on the mass. So basically this force is directly proportional to the velocity of the mass, right? This is directly proportional to the velocity of object, you can say, right? So therefore this fd is equal to minus d times and minus d times dy by dt. Why I am taking here negative sign? Because this force always opposes the velocity, right? So opposes the velocity. I mean to say it will work on the opposite direction of the velocity, right? If velocity is working in upward direction, then this force definitely will work in downward direction. So this negative sign shows this, that this force always oppose the velocity of the object, right? Now where here d is positive constant and we called it damping constant, right? Called damping constant. So now the last force which will work on this system is the external forces. All the rest external force, sometime we may call this force as a driving force, right? So the total driving force here, let us say this force is Fe, right? So the driving, that is the force acting on the mass to displace the position of the mass from the equilibrium position. So the driving force on the object is, let us say it is represented by F suffix E for external forces. So let us say this is F of T. So finally what happened? The force, total force which are which is acting upon this system is capital F. The total force, or you can say net force, right? Acting on this acting on the system is what? Summation of all these four. So we can say F due to gravity plus F due to spring plus F due to damping force, due to that means the medium, and the external force. So now using the equation 1, that is the Newton's second law of motion, we can write the equation now. So therefore equation 1 become, right? Equation 1 become, that is MA, that is d2y by dt square is equal to the sum of all forces, that is the net force. So Fs plus f of d, not f suffix d, Fe, right? So here this force is what? Mg, force due to gravity. Now Fs due to this spring is what? Minus ky minus mg. right? So here this is minus k times y minus mg. Now, due to the damping, we have d into dy by dt plus the total force, external force. Now here we can see this mg and mg will cancel out, right? So this mg and this mg will get cancelled. So what we have now, we have the m y double prime minus minus plus d into dy. If you are writing it in prime notation, so d times prime only, right? So here we will have what dy prime plus k times y is equal to f of t, right? So we have this equation, and this equation is known as spring equation, right? So this equation has a special name we called spring equation, right? And this is the governing equation, which is, we can write here, which is the governing differential equation of the mass spring system, right? This is the governing equation, right? So question is what, from this equation, right? From this equation we can analyze this equation, and to if we analyze this equation, what will we have? We will have the solution, and that solution will describe our motion, right? This solution of this differential equation will analyze the motion, right, of this mass spring system, right? So under different condition, we may have different motion, right? Sometime this d will be 0, sometime this f will be 0, right? So under certain condition we can classify the motion, right? So now we are now classifying this motion. So this is the last part we are going to discuss here, right? So therefore the classification of motion is what? Classification of motion, because this is important, because in the problem, in the real life situation, we will have this condition, and in which condition, what kind of differential equation we have, we need to know. So here I am classifying through this graph, right? Suppose we have ft, that is there is no external force. What happens when there is no external force? I mean to say, this vibration is just due to mass only, right? So in this case we say this vibration is free vibration, right? This vibration is free vibration, or you may called free motion, right? Or sometime we may use the word oscillation, right? So free oscillation, when there is no external force, right? Due to absence of driving force, we call free vibration. Now, when we have some external force, that is when f of t is non-zero, we called it forced vibration. Force vibration, right? So whenever there is in the statement, if it is written this is force vibration, you need to understand this ft should not be zero. Now now we can classify further this these force vibration and free vibration in further category, right? So what happened when d is 0, right? So that means when d is 0, that means damping constant is 0, no damping. That means no damping force. It means this is the absent of friction, or you can say the resistance, right? So this is actually undamped motion. Undamped, right? That means we are considering the force due to the medium is 0. That means undamped motion. Now, the second case is what? When d is not equal to 0. That means we are considering the force due to medium, friction or resistance due to medium. In this case, we say this is damped motion. Damped motion. Further, this motion also can be subdivided in three parts, right? So this motion can be subdivided in three parts. First is what? Overdamped. Overdamped. Second, that is critically damped. And at which point or in which condition we say this is overdamped and critically damped, we will discuss through some example. In the coming video, we will discuss each of the case through some example, right? And there we will discuss in which case, in which condition we say the motion is overdamped, right? And what will be the nature of the solution, we will analyze through example, right, in coming video. And the last part is what? Underdamped. Underdamped. So now suppose the motion is free damped. It means ft is 0 and d is not equal to 0. So accordingly you will decide the differential equation, governing differential equation. Suppose the motion is free damped, undamped, right? That means undamped free motion. It means d is 0 as well as ft is 0. So accordingly you will decide the differential equation, right? So I hope you have enjoyed this session, and please comment in the comment box which part of this discussion you like most. Thank you very much.